Hi everyone, and welcome to our lecture video on section 1.6, a couple of differentiation techniques. We're going to talk about the product and the quotient rules. So the objectives here are pretty straightforward. We're going to start just by learning both of those differentiation techniques, and then towards the end we're going to use some of those techniques to differentiate average cost, revenue, and profit function. So there's a little bit of business application towards the end of this section. But for right now, we're going to start at the bottom of page 1 with theorem 5, which tells us the product rule for derivatives. So we're going to start by letting capital F of x equal a product of two individual functions. So the overall function is f of x times another function called g of x. Then if we want the derivative of capital F of x, so that's f prime of x, we take the derivative of that product. We do so by taking the first function, the first factor f of x, times the derivative of the second function. And then we're going to add the second function times the derivative of the first. So in words, and the way that I kind of remember this and what I would suggest to you, don't try to memorize as far as, the F's and the G's. That can get quite cumbersome to memorize. What I think about instead is think of this product rule verbally, and it's a lot easier to remember. When you look at this, think of the first and the second piece of the function. So again, first and then the second. And so the product rule tells us to take that first times the derivative of the second, and then we add the second times the derivative of the first. And again, when I'm saying the first and the second, I'm just talking about the individual factors that make up the overall function. And we'll go ahead and illustrate that with our first example. So I'm going to turn over and move to the top of page 2 here, and we're going to take a look at example 1. They ask us to find the derivative of this product function. So notice the overall function is made up of a first factor. You can think of that like your first individual function. It's x to the fourth minus 2x cubed minus 7. And then we're going to multiply that with the second factor, or the second function, which is 3x squared minus 5x. So we're taking the derivative of that overall function. This is going to equal the first factor, which is x to the fourth minus 2x cubed minus 7, times the derivative of the second. So when I look at this second piece of the function, 3x squared minus 5x, I can just use the power rule to find its derivative. So the 2 comes down and multiplies with the 3, so that's a 6x. Notice the exponent of 2 goes down by 1, so it's just 6x to the first power. And then minus the derivative of 5x is just 5. So what I've done so far is I've taken the first factor times the derivative of the second. Then it's going to be plus, and now we do just the opposite. Now we need the second, 3x squared minus 5x, times the derivative of the first. And the derivative of that first factor, again, just using the power rule, is going to be 4x cubed minus 6x squared. And the derivative of that 7 is just a 0, so that derivative is done. And at this point, we've actually got the derivative. It's just a matter of doing a little bit of algebra to try to simplify things. So to start here, x to the fourth, I'm going to distribute to each term in this other factor. So x to the fourth times 6x, x to the fourth minus 5, and then we're going to take things from there. So let me go ahead and start jotting down some results here. That first term is going to become 6x to the fifth, and then I'll have a minus 5x to the fourth. Once that's distributed, you can cross it off if you'd like. Next, I'm going to distribute a negative 2x cubed times 6x, so that's a negative 12x to the fourth. And then I'm going to distribute all the way down to the end, so that's a positive 10x cubed. And then finally I need to distribute the negative 7. So that's a minus 42x and a plus 35. Then towards the end, when I look at the second group, I'm going to start by distributing my 3x squared. So that's going to give us a total of 12x to the fifth. So I'm going to jot that down, 12x to the fifth. When I multiply to that last term, I'm going to have a negative 18x to the fourth. And that one's done, so I'll distribute my negative 5x. So that's a minus 20x to the fourth. Oh, I'm almost running out of room. I think I'll get that last term in. And then I'm going to have a plus 30x cubed. So plus 30x cubed, and we just barely made it. So we've got all the terms written down. And really at this point, we're just going to go through and combine some like terms. Start with your largest exponent and work your way down. So I've got 6x to the fifth, 12x to the fifth. That's 18x to the fifth. I like to cross these off as I go so I don't accidentally miss anything or add something in twice. Next, I'm looking at my x to the fourths. So I've got negative 5, negative 12, so that's negative 17. Let's see, we've got a negative 18 here, so we're up to a negative 35 minus 20. Looks like a negative 55 x to the fourth. I'm going to cross all those off. There are a bunch of those. For the x cubes, we've got a 10x cubed, a 30x cubed, a total of 40x cubed. Cross those off. And then our final two terms, minus 42x plus 35, and that whole thing makes up our final answer. So the real work, I feel like, with that example and with a lot of these examples that we're going to encounter is not the calculus so much as the algebra. So again, that's an illustration of what we call the product rule for derivatives. Next, we're going to learn what's called the quotient rule. And as the name indicates, this is useful for finding derivatives of quotients or fraction functions. So let's start by defining a function q of x equaling n of x over d of x. They're using n and d here for numerator and denominator. Then the derivative q prime of x is equal to d of x times n prime of x minus n of x times d prime of x, and it's all divided by d of x squared. Now again, I don't recommend looking at this as a formula to memorize with the n's and the d's and everything else. I'll give you a little trick here to help you remember this so-called quotient rule. It's kind of a silly little expression, but once we understand what it means, it can really help us remember exactly how the quotient rule works. And I'm going to write it down as I say it. But I always think of the quotient rule as low d high minus high d low over low low. And again, that sounds kind of silly to say it, but if you think about numerator denominator, numerator is the high function, denominator is the low function. So again, when you do this, take the original low function times the derivative of the high function, denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator, divided by the denominator squared, the denominator times itself. Another thing that's really important here, because the numerator involves subtraction, we have to make sure to get this order correct. One way to help with that, notice the overall denominator and overall numerator, they both begin and end in low. So if you ever get confused about if you start with high D low or low D high, just remember that denominator begins and ends with the low function, as does the numerator. So let's see exactly how this works with example 2. So I'm going to move over to the top of page 3. Example 2 tells us to differentiate the function f of x, which is equal to x squared minus 3x over x minus 1. Again, you want to think of this as your high function and your low function, numerator and denominator. So this overall derivative, f prime of x, this is equal to low d high minus high d low all over low low. And after you commit that little phrase to memory, this quotient rule really starts to come together and works out pretty well. So the low function is x minus 1 times the derivative of the high function. So the derivative of that numerator is 2x minus 3. And then I've got minus, next it's high d low. So the high function is x squared minus 3x. D low here is just 1. And then in my denominator, it's low, low. So take the original denominator times itself. X minus 1 times x minus 1. And then, of course, just like with the product rule, we're going to use a little bit of algebra here to clean this up and just simplify our overall final answer. So in that numerator, we're going to do some distributing or foiling. So x times 2x is 2x squared. On the outside, I've got a minus 3x. Inside is a minus 2x, so that's a minus 5x total. And then plus 3 for the last. Now be real careful with this second portion. Whatever I need to multiply or distribute from the back combines with distributing or multiplying out the negative. Now, in this example, it's not a whole lot to distribute because that d low portion was just a 1. But if you were distributing, 1 times x squared is x squared, then distribute the minus. So it's a minus x squared. Likewise for the second term, it's a plus 3x. Now, in the denominator, we typically do not want to FOIL that out. We're going to leave that in factored form, and you can just write it as x minus 1 squared. Typically, where the real work is going to be involved is in this upper portion, this numerator. The denominator, you write it as the low function being squared, and that'll either reduce later on or it doesn't, but you do not need to FOIL that out. That's counterproductive. So in that numerator, 2x squared minus x squared is x squared, minus 5x plus 3x, so that's a minus 2x, and then plus 3 at the end. Again, that denominator, leave it in factored form as x minus 1 squared. The only thing we would investigate here at the end is to see if that trinomial in the numerator is factorable. In this case, it's not. The only factors of 3 are 1 and 3. Those are not going to add up to 2 in the middle. Remember, if that's a plus on the constant, those factors would have to add to the middle term. So this does not factor or break down any further. That entire expression is our final answer. And again, that illustrates what's called the quotient rule for derivatives. Now, I'm going to scroll up. I actually want to add a quick example here off in the margin. And I'm going to give you the function g of x, and this is equal to x squared minus 3x over x. What I want to illustrate with this little side example is that the quotient rule is not necessarily always useful when it comes to these fraction functions. It depends on the denominator. So in our previous example, example 2, the denominator was x minus 1. It was a binomial, had multiple terms. In the current example, notice your denominator is a monomial. It's a single term only. Now, we could differentiate this using the quotient rule. It would work out fine. It would give us the correct answer. But I think the better approach, anytime the denominator is a monomial, if it's a single term, then I think you're better off simplifying the original function ahead of time and then finding your derivative. If that's a monomial, you can split this fraction into 2 separate smaller fractions, keeping that common denominator. In this case, I'd write x squared over x minus 3x over x. Notice each one of those individual fractions simplifies further. So x squared over x is just x, minus 3x over x is just 3. Now that we've simplified that original function, it's much easier to find its derivative. So g prime of x is equal to just 1 according to our power rule. Again, you could use the quotient rule on g of x, but it's a lot easier to do the simplifying first rather than relying on that quotient rule. And then I'm going to stop here for the part 1 video. In part 2, we're going to move on to the bottom of page 3, and we'll look at the business application associated with section 1.6. So we'll pick up there.